Does it automatically record?
Yes, I have set it so because I forget it. So I made it so that unless I force it, it will record immediately. Let's see. This is. Oh, Rob. Boom.
Swingers book?
What's that?
So we see you got Swingers book?
I've had it for about a week or so.
So it's not a book from 20 years ago?
No, it's actually, it's brand new.
Yeah, so you got your book.
Now trying to find the book for math methods, just because I thought the Morse.
What's the book I suggested for?
Methods of Theoretical Physics.
It's a suggestion, right? It's not a textbook.
It was on there. There was no required book. There were just resources.
Yeah, exactly. So I would say Morse and Fishback is it's a great book to have if you are going to be doing physics. It has everything in it, but it's a little more than what you need for the course. So if you're tight budgeted, I would say that's one thing you can leave aside. But if you want to invest on something that you would use it for life, it will never go out of content, then that's the book to depend on. Did I convey the point?
Oh yeah, it was one of those that since I was watching the lectures and all, I have an Arfkin book.
That should be good enough. As far as a textbook goes, that should be good enough.
It's a third edition.
Yeah, doesn't matter. Most of the content, I mean, 80 to 90% of the content remains in all these books. I mean, in fact, you can use this also for math methods. You'll be surprised how much of I use the content of this in math methods. I'll change the story, I'll change the content, but that's Michael.
But the Morse book, I found it for as much as $600.
Yeah, you still are good. Tell that again? Yeah, it is expensive. I agree.
Well, they do have a Dover book. They stopped printing it in 2018.
I see.
And a lot of places you can only get volume 2. I looked at the interlibrary loan, and you can get volume 2.
Even in interlibrary loan? I think maybe it is a circumstance that is changing the scenario. Morse and Fishback, I would expect it to be there in every library. Like it's such an old book, first of all, and it's such a classic that I expect it to be there. Any serious library should have the book, and Morris Library is a pretty good one.
Well, when I first saw when I looked it up and I got a stock cover, picture of the cover, and I think it must be, I have an old, there was a Milford Christie book. But
Other again?
Christie and Milford.
I'm not aware, but that doesn't mean anything. Don't assume anything.
But it has the same binding. And so when I saw that binding, I thought, wait a minute, I've got that book. And so I went and checked everywhere, and because we had one of the professors at SIU retired, and I was his TA for several classes, and he just gave me this box of books. He said, because he was going down to Florida to run a hotel with his wife and daughter, and he said, here.
That's nice. Yeah.
And he says, you might use these.
Check it out. Maybe you will find them in some corner. Right? Sometimes when you get this bundle, often there is something hidden in the corner. So check it out. But Morse and Fishback are from MIT. So I think right after quantum mechanics came over, like before that there was electrodynamics, of course, in the late 19th century. But electrodynamics was, hello, Alia. Hey, Jordan. So we are more in number here. So it's going in the right direction, I suppose. But I was telling, yeah, so when electrodynamics, the differential equations were vector differential equations, so it was a little harder to deal with. And quantum mechanics suddenly brought in a scalar differential equation, and there was a lot of applications for it. So Morse and Fishback was one of the first person to really classify all this differential equation, what are the solvable ones, what are the not solvable ones. And they really did a great job. And this was probably, I think, done under the direction of Stratton. He was the leader in electrodynamics at that time. So there's a lot of electrodynamics also in there. But then Jackson came and these books, they're still classics, no doubt about it. Everyone knows about it. But at least graduate studies, you depend a lot on Jackson, which is great. And no doubt about that. It's just that everyone studies Jackson and no one studies anything else. So that's the only complaint I have with Jackson. That they monopolized it in a sense, but they do a good job. They did a good job with it.
The only hard copy home.
Yes, probably since I see the number of people increasing here, so maybe we are going in the right direction, even in the number of cases, maybe that's why everyone is showing up. So that's all good. I like to see phases. I think when Jordan shows up here, maybe that's the time to assume that everything is normal. But we cannot have Khaled here, I suppose. Maybe that's perfectly normal, right? If he shows up here, that means it will be perfectly. Okay. Any comments or anything you wanted to say about homework or anything else? So, oh shoot! Again, I didn't bring that pen. I think last time I left one. Yeah, so I made some progress in plans until midterm 1. So homework 2 will be due on Friday. Homework 3 will be the first, so let's say electrodynamics oriented homework, and this will be due the next Friday, September 11 Friday. And I noticed that the Monday, so we'll have only one class during this week because September 7 is a holiday. That is visible. Am I right? And this will be on Maxwell's equation, relatively straightforward, basic ideas of starting from Maxwell's equations. And midterm 1 is the Monday following that, September 14th. That's sort of the plan, at least until midterm 1. And except for midterm 1, I think everything is posted, I suppose, at this point. Midterm 1, I haven't made any plans yet. If there is going to be a component of take home, you will get to know in the class. Sometimes what I do is, if there are 4 questions, 1 or 2 questions, I make it available before, let's say 3 days before the exam. So you work on the problems and bring the solution to the class, and then you work only on the rest of the 2 questions in the class. So it's partly take home, partly. So it has worked out well in the past, but that also means that I have to come up with a reasonable question which can be explored sufficiently at home. So, okay, so there was I was reading your responses in the extra credit on Friday. Most of you tried this integral. I was glad that you guys did try. So this was dx. I had a move, right? Move the camera. So this was, I did the following integral. We were doing, showing that the representation for delta function does satisfy the condition that we could 1, and we tried to show this is equal to 1. So this was done in the class, but then we said that, oh, maybe we should also be able to do for any b, let's say less than 0 and a greater than 0. Well, let's just say a and b, a and b, dx epsilon over x squared plus epsilon squared. So I like most of your answers, but I think Rob, you got you could actually show that that's equal to 1. That's nice. So basically, I thought I think I use Rob's idea. Just do the integral, forget that a and b, so you just do it as an indefinite integral. Right? So this is tan inverse of x over epsilon. Is that what it is? I think so, right? Right? Yeah. Okay. And then substitute, and then there is limit, right? Limit epsilon tends to 0, and then there is a to b, which is the same as limit epsilon tends to 0 of tan inverse of a over epsilon minus tan inverse of b over epsilon. Epsilon tends to infinity, so this will be tan. If a was, let's say, if from here to here, let's assume a is greater than 0, b is less than 0. Then I have a greater than 0, so this is epsilon tends to 0. This is plus infinity, right? Tan inverse of plus infinity is pi by 2 minus of tan inverse of minus infinity, which is minus pi by 2. Okay. And what happened to the pi? Oh, there's a pi. Here, right? Pi. But I like your solutions. All of you guys tried in the right direction, explored, thought about it, and you wrote so. So I liked your works actually. So thanks. So yeah. So in the same direction of delta functions, let's do a little bit more of delta functions. I'll do this very briefly here. In the second semester, we'll again see delta functions being used in a more explicit manner. Here, it will be more of a it's a handy tool, but probably not necessary. In second semester, it will almost turn out that it is necessary in the sense that you might not be able to proceed otherwise. So let me do a little bit of delta functions, starting from what we did last time, the delta functions. And as far as we are concerned as a user, so we introduced the idea last time as a concept, 0 everywhere, infinity at one place, but it is in such a way that integration has to be equal to 1, so that gives some structure to that infinity. You know that infinity cannot be anything; it has to go like 1 over the volume. So that's one thing. So, but that's the idea. As a user, what we need to know is that minus infinity to plus infinity dx delta function is equal to 1. So that's all. In fact, as we showed, this could be anywhere surrounding the 0 point, and that is also equal to 1. If that's the case, we can immediately, so that's our, as a user, that's our identity. And then we extend it a little further. Let's say f dx delta x f of x. And what would that be? So that's the next thing we realize. Notice it's a product of two quantities. Delta function is 0 everywhere. So, and integration means sum. So you're summing up a lot of quantities, but it's 0 everywhere except at one point where it is expected to give you 1. But at that point you have, so this is pretty much, yes, discussion.
Is it f of 0?
That's f of 0. That's exactly correct. In fact, we can also say this, so this is, since it is 0 everywhere, we can in fact say, write it in this form too. And that's equal to 1. Okay, why? Because this doesn't set. I mean, everywhere else it is 0. How can it contribute? So it is f of 0 times this, that's equal to 1. So this is also f of 0. Right, so that's slightly more general than the first step. Why should the delta function be evaluated at x equal to 0? It doesn't have to be. So this is also possible. You would say this is the x delta of x minus a times f of x. In fact, you can begin by saying f of x is 1, and that's also very true. So this is nothing but f of a. In fact, this is what we will encounter most of the time. This is very general. That's some of the if you want, that's an integral. Usually when we are studying calculus, the simplest integral we say is x raised to n. The integral of x is x squared over 2, or maybe exponential is a simple integral. So this is in fact the easiest, right? Just use that function itself in a sense, but it is not clean. Remember, delta function is not a good function. Not everyone likes it. There are issues related to that in the sense that is it a well-defined function? So, but we have to deal with it because we deal with charges which exist only at one point. Okay, so that's good. So now we want to extend this a little. So let's say we would like to know what is this now? The x delta of, let's say we multiply something out. So it's b of x minus a times f of x. Right, so that's what we would like to do, and we will notice that, I mean, actually we don't need to do develop anything new. We have most of the information here itself. Have you guys encountered delta functions before? Used delta functions before? So,
Yes.
okay,
Yes.
so any answers for this immediately? If
I don't know the answer.
It doesn't matter, but
Is it f of a over b
f of
over the modulus of b?
that's
You just set
correct.
it equal to 0, and
Tell that again.
you just set it equal to 0, and then it's a over b, f of a over b.
F of a over b, that's correct. That's correct, but Avinash said there's something more to it. So that's what one would expect. So how did you get that? So you set this to equal to 0, right? Bx minus a equal to 0. That's when it contributes. But then there is something more to it apparently, and Avinash says it is magnitude of b, and that's correct. But then we won't figure out how did he come up with magnitude of b there. So let's explore this a little bit. And once you have this, we will be able to put in almost write a general formula for any function. What if there is a function in here? And we would like to say sine of x inside of this. Right? And we should be able to do that. And we'll come to that. But let's do this simple one to begin with. Let's call this I. Let's do a simple steps to evaluate this. So I, we simply substitute y is equal to bx minus a. And then I dy would be equal to b times dx. That's how you would proceed. So the integral I is equal to, I have to do two things. I have to replace this dx, and then I had to replace the limits. Okay. So check on me if I'm doing everything correct. This is dy over b, right? That's dx. Dx is dy over b. And then I argue, here check on me, right? Y is bx minus a. So x is minus infinity. So when x is equal to minus infinity, what happens to y? Right? I asked that, and let's say x tends to minus infinity, and when x tends to plus infinity, what happens to y? Right? When x tends to minus infinity, I argue that y goes to minus infinity. Is that right? And if x goes to plus infinity, y goes to plus infinity. Am I correct? Check on me. dy over b and delta of y and f of x is y plus a over b. Is that correct? Okay. Seems like, but there is a small mistake I made, but we'll see. Proceed. Okay. So that's equal to 1 over b times minus infinity to plus infinity dy delta of y f of y over b plus a over b. But I know the identity that if you have a delta function of y times f of y, I just have to set y equal to 0 inside the function. So I'll set y equal to 0. And that's 1 over b. And this is f of a over b. Right. That seems to be all fine. But Avinash studied this magnitude of b. Why did we not get a magnitude of b there? Or maybe Avinash is wrong. So if we made a mistake, why did we make a mistake?
We're assuming that b is positive.
Good, very good. So then I say this, when x tends to minus infinity, y would go to minus infinity only if b was positive. If b was negative, this would flip sign. Right? So this is actually has two values. If b was greater than 0, and this is plus infinity if b is less than 0. All right, so it's two limits in there. So this is minus infinity. Okay. But this remains the same. What would change now? So this is all for b greater than 0. Let's say this is all for b greater than let's do this again. Less than 0. So that's for I being greater than 0. So I is equal to, we do the same thing again. So dy over b. This assumes that whatever that value b is, so now b is negative. B is negative here. Right? So the negative sign is implicit in that variable. But now the limits, we have to say this is plus infinity to minus infinity. The limits change, and rest everything remains the same. I use the idea that if I swap the limits, the sign of the integral changes. So this is minus 1 over b, and rest of it remains the same. So that's f of a over b. So this is if b is less than 0. So if I combine these two together, then I know that this is the right way to put it. Notice the magnitude of b doesn't show up inside the function. Pretty straightforward. But it gives you the idea that, oh, so substitution is the way to go. Right? Whenever I have a delta function inside, or set the argument of the function to some value, that is how you would evaluate the delta function. So that's good. So now let's do another. So this kind of takes care of all linear functions. So what we're saying is that any linear function we have set dx minus a is equal to 0. So that's equal to x, so equal to a over b. And that's what it evaluates, and the coefficient gives you the coefficient of x gives you that value. So now let's go to the next case. So now let's say we have an integral I, which is the form minus infinity to plus infinity dx, and first of all, let's make it simple. So this is x squared minus a squared, and this is f of x. And we want to again work on this, but the idea will remain the same. We want to work in this form, and maybe I should go back here and say something a little bit. Notice that this integral would have worked fine even if even this would have worked, a over b minus of some let's say epsilon, and a over b plus epsilon x delta of bx minus a times f of x is still equal to this, because the only thing I need to is I need to capture that function around that point. I don't care what happens somewhere far away, as far as it doesn't go to infinity. If it goes to infinity, then I have issue. But if the function is smooth and simple, this is also okay. So maybe I should add resumes the function is well defined everywhere. Well defined means it is not infinity, or it doesn't all the calculus rules work. That's primary, right? So that's a sloppiness there that you don't care for what kind of verifying. So that's the sloppiness of the whole thing that's going on here. Okay. Any questions on that? So if that is the case, I come back to my equation here and I ask, where does this go to 0? Apparently this goes to 0 at x square minus a square is equal to 0. That implies that x is equal to plus a and x is equal to minus a, right? There are two roots of that equation. That's where it can go to 0. So my integral I at those 2 points is again I have to go minus infinity to plus infinity, but I use that idea there that this is minus a minus epsilon, where epsilon, let's say limit epsilon tends to 0. And this is minus a plus epsilon, the x, delta of x squared minus a squared, f of x, plus same limit, but it could be epsilon 1, epsilon 2, doesn't matter as far as I capture. It's plus a minus epsilon. Right, that should be clear. We just used the earlier fact. And now let me write this more explicitly. This is limit epsilon tends to 0 minus a minus epsilon minus a plus epsilon dx. And this is delta of x squared minus a squared. If I were to write it in terms of the roots, it is x minus a and x plus a. And the x plus limit epsilon tends to 0 of plus a minus epsilon plus a plus epsilon. Again, the same idea, x minus a, x plus a times f of x. Any questions there? What is the first integral equal to? Any thoughts on it? Is that doable still? I claim that it is doable now. We have all the tools to do that. Maybe not very obvious. Let me go one more step. Okay? It seems like I didn't do much. Okay, so let me do something. So this is evaluated at x minus a, right? Yeah, so let's substitute x minus a here in this part of the integral as x minus a is equal to y. Let's substitute that because we expect this, no, x plus a. Because that's where this will contribute, right? X equal to minus a, this contributes. So I substitute x plus a is equal to y here, and I substitute x minus a equal to y there. If you think you're getting confused with y, so you can put y prime there. Those are different integrals. That's equal to, again, limit epsilon tends to 0. So this is what? So when x is equal to minus a, this goes off. So this is minus epsilon to plus epsilon. dy is the same as dx. and I have delta of x minus a, but x is y minus a. So it is y minus 2a. So it is y times y minus 2a. So, and x is y minus a. Resume. Plus limit epsilon tends to 0, and here it is again dx is the same as dy, but now when x is equal to plus a, again this is minus epsilon to plus epsilon, and delta of x minus a is y, and this is x plus a, so it is y plus a, so y plus 2a. Okay. So this, I said again, that is one is minus 2, one is plus. So clear, that's very algebraic, but geometrically what we are actually doing is, there are 2 points where this function goes to infinity. So this is, that shows that it's going to infinity. This is x, this is 0, that's minus a, that's plus a. So first I'm integrating from here to here, and then going from here up to here. So that's what it's, I'm trying to do, but these are algebraic manipulations to capture it. Since it is really small, I'm taking the limit epsilon tends to 0. Right? In this region, once I have moved this to 0, this doesn't go very far, right? This y minus 2a stays 2a. Within this limit here, notice what's happened. So y goes from minus a to plus a. That is touching the infinity. But this one goes from when y is minus epsilon, so this is minus a minus 2a, to plus epsilon minus 2a. So this quantity is not going to 0 anytime. Right? This is pretty much minus 2a. Is that clear? This is y is what is taking this argument to 0. It is not the y minus 2a that is taking it to 0. And same thing here. This argument takes it to 0. It's not y plus 2a. Right? And one can see this right here itself. The next minus one of the factors in that root. The function can be represented in terms of product of roots, like a quadratic equation does. And so this quantity stays minus 2a. You don't have, and if I realize that this is simply minus 2a, I can use this principle to just write it in the denominator. So that is a leap here. Write it. So see what I'm doing. So this is 1 over 2a magnitude, because that's the coefficient of y. And this is evaluated at y equal to 0, so that's f of a. No, f of minus a. Same idea here, plus 1 over 2a magnitude again, and this is f of plus a. Is that clear? What I did, any questions? So I think from here to here, it was not completely algebraic. I kind of used some interpretations. But is that very clear? Any questions in that?
I don't know that I quite followed it, but
Okay. No, good. Okay, so I just need one response that I can repeat. Okay, so let me repeat this. Notice this delta function will get activated if you want, if I use that language, whenever this goes to 0. and you ask when does this go to 0 within this limiting factors, and you say that this never goes to 0. You realize that between minus epsilon to plus epsilon, this never goes to 0 because minus 2a minus epsilon and then 2 minus 2a plus epsilon. And remember, even whatever value of 2a is, I can always find epsilon that is smaller. It will never work that the other way, unless a is 0 to begin with. Right? If a is 0 to begin with, what happens? Then we do something else. Oh, extra credit. Right? What happens if, instead of me thinking here, you guys think, what happens if one of the roots is 0? So I'm very quickly going to say many roots, or what happens if one of the roots is 0. It should go through that way also, but it's just that whatever I'm stating doesn't go through. Okay? So again, the realization is that delta function contributes when this is 0, and you learn that only y equal to 0 happens. This never goes to 0. This is equal to minus 2 in the limiting cases. Once you realize that, so maybe I can write this in the second step. Okay, so using that argument, I say that in the limit epsilon tends to 0, this is actually delta of y times minus 2a. This is minus 2a times f of y minus a. So this is again y limit epsilon tends to infinity. Sorry, it tends to 0. And I did that plus limit epsilon tends to 0. And this is y times 2a, positive f of y plus a. And now we know how to do this because this is of this form. But here, if I set a equal to 0, then it is b times x. Right? And this is like b times x, or b times y here. So now I know how to do it. I just have to evaluate in the denominator. So that's equal to magnitude of whatever is sitting there. So I say that's 2 times a. And evaluate this at y equal to 0, that's f minus a plus 1 over 2a times f of plus. Any questions? Did that help? Okay.
Yeah.
Yes. Okay. Okay. That's nice enough, but I want to write this in a slightly different form. Correct. So we go back here, right, at this stage, right, and let's see. So x squared minus a squared is equal to x minus a times x plus a. Right? Pretty straightforward. Any function, in fact, if you know the roots of the function, you know the function itself. You can write it as a product of x minus a, x minus 2, x minus a. It's a pretty nice theorem, because if you think about it, what you're saying is that you have this function, and if you know when this goes to 0, you know the whole function. That's a strong statement there, right? If you know these 3 points, when the function goes to 0, you know this whole behavior. So if you know 10 places where it goes to 0, and that is only where it goes to 0, you know the function. It's a more pretty big statement if you try to think about. But okay, so that's good. So I want to write this as like use this idea basically, because if I know this point, so it seems like this point has the whole function in it. So I want to write it in terms of these 3 points. Right? So I say that this is equal to here. Yeah, so let's do the following. Let me take the derivative of this function. So let's, whatever this function is, d by dx of x squared minus a squared, right, square brackets. Since I have two places where x shows up, I can either hit here or there. When I hit here, that goes away. So that's x plus a. And when I hit the second one, that's x minus a. So kind of taking the derivative isolates this roots if you want, right? But I want to do something more than that. I want to write this as, let me actually go back and write this as g of x. And I want to write it in terms of the function itself. Right? So the derivative of g of x, derivative of g of x is equal to, this is not the function itself. I want to multiply by x minus a and divide by x minus a. Seems like a trivial exercise, but let's do that. X plus a over x plus a. Again, I'm doing the idea that I want to do something about the points. The value above there is the function itself, f of x, no, g of x. But now I change the story. So x minus a is the derivative of the function at x equal to plus a, right? If I were to take the derivative of the function at x equal to plus, can I capture this somehow? What am I saying? Let me write it as x plus a. So this is g of x over minus a plus a. Can I do this? Yeah. Now I go back actually. I think I implicitly said that, but I think I was not very clear. So now notice what is dg over dx, the derivative of this, at x equal to minus a. And what is the derivative of the function at x equal to plus a? And that seems to be, if I had x equal to minus a, this goes away. The derivative is this. X is equal to, no, this goes away, so x minus a remains. Right? And this one is x equal to plus a. This goes away. And it is a plus a. It is minus 2a and plus 2. Okay. What am I saying?
So what's your goal?
Yeah. Give me 1 minute more, okay? And then maybe I won't have to say the word. Almost here, I just want to write this as derivative. So what I want to write here is that I'm probably confused is derivative of x is f g of x g of x, and then I write this as derivative of g of x at x equal to around x equal to a, I suppose. That's what I want to write about. Okay.
Are you trying to show the integral is equal to the sum of function evaluated at the root over the differentiation of function?
That's correct. That's what I'm after. Yes. So, okay. So, guess I'm not. Okay. How about this? Let me stop here. I think this is too general. I'm not able to make this. So, but you see this pattern here, right? So let's leave here, and then let me go back and try to evaluate this again. Oh, I shouldn't have probably evaluate that. Erased everything. Yeah. So let's see this as what we got as the answer was f of minus a, right, over it was minus 2a, but then I took the magnitude of that, which made it plus 2, correct? And this is plus of f of plus a over plus 2a, and then I took the magnitude of that. Okay. But notice what is happening here. Plus 2a is nothing but derivative of g with respect to x at x equal to plus a. And yeah, derivative of this. Did I write this part? Derivative of f x equal to plus a. I think this is opposite. No. Did I do this part? At x equal to derivative of g of x plus at x equal to minus a. Again, okay, at x equal to minus a, right? So I'll do this. So this is what I will be remaining with. X plus a, that should be plus 2a. No,
because you can also write dg dx as 2x.
of course.
Yeah.
Of course. Oh yeah, that's the best way to do it. Thank you. Okay. 2x and then x equal to minus a. Okay, thank you. That's it. Okay, otherwise I'm not confused. Okay, so this is minus 2a, and I guess, okay, so that's what it is. Okay, so the way I will write this is f of first root here minus a. I was trying to motivate that, but I'm not sure whether. So let's call this g. X. G over x. And evaluate this at x equal to minus a, right? The same value as here. And then you take the magnitude. Plus f of plus a. I hope I'm not missing something tells me that I'm missing. This interchange. Okay, so this is the same as sum over the roots. There are only two roots. Let me say r equal to 1 to 2. R means R stands for roots. Find the roots of this function and then evaluate that. So this is f of xr. This is the first root, second root, and so on. Divided by I could do this better, I could motivate this better. It seems like I stated that I can get it from here somehow. But that's good. So at least I did that explicitly earlier, and then I realized that, oh, this can also be thought of as a function evaluated at the root divided by the derivative of the argument of the delta function evaluated at the root. So in general now, so now that is we make a big step forward, and that is we write this as any function. The x delta of g of x, think of it as sine function, right? Sine function has infinite roots in that. It goes to 0 at many, many places, times f of x. Immediately you say that any function g of x can be written as a product of its roots. Now r is equal to 1 to n if it has n roots. If it has infinite roots, still it works. And this is ax minus xr. You want to be a little careful because at x equal to 0, it should give you the same value of the function. So that is also one more thing you want to add on to here. Let me just say r. I think that's better because it could have infinite ones, but in general, r equal to 1 means n is okay. You can count the positive ones also. And let me also put a constant a, just so that I can catch x equal to 0 case also in there. Okay. I think that is okay. Maybe I don't even need this a that x equal to 0 as x of 0 as that. So probably that's not needed. But I'm thinking of a quadratic equation, ax squared plus bx plus c. And if I have this, then I need to get this a out, right? So this will be x minus x1 times x minus x2, right? I need to pull this a out, I suppose. And so I think I need to have this a out.
I think that is just a factor. Like,
Yeah, of course. But I was trying to say, is it necessary to put that a, or can I survive without that?
I think you can survive without it.
What if it was a quadratic equation? I
I
need
mean, if we have x minus x1 and x minus x2, there's no need to have a. What a does it takes x squared plus, let's say x squared plus 4 to 2x squared plus 8.
But what if I
it is.
have such a function? Then this will not capture it, right? Without the a. I want to keep it general.
I think x minus root should give like a quadratic equation.
No.
Should it not?
Will it?
I think there's no need to put a.
Let's check. Okay, extracted. I think no. So what you're claiming is that if I have ax squared plus bx plus c, right? If I have f of x is equal to this. This is the same as x minus x1 to x minus x2, right? Where x1 and 2 are minus b plus or minus b squared minus 4ac. Correct? Is that what you're saying? No, right?
That can't be.
I won't get that. I won't get this a. What I will get then is basically this will be, let's say, f1, and f1 would be x squared plus b over a times x plus c over a. I think that's it. I think so. Isn't that right? Check. Okay,
You can get specific. You can't get a general. You can get one without an a. You can get a general.
Because I think the roots are evaluated at equal to 0, so I can always pull that a out. It doesn't matter.
Yeah.
Isn't that function the same as ax squared plus bx plus c? It's just a factor, right?
Yeah, but the factor is important. Right. If I set it to 0, that is not important. But if I have the function itself, then that factor has a meaning. So I think.
But if we're taking, if it's the parameter of the delta function, don't we only care when
No, because it here it contributed, right? B, that magnitude of B contributed there. So this will contribute. So
one thing that worries me about the statement in the product is it seems like you're giving an A every time. Is that, so
no, right? This is F. So right? This is a coefficient, right? This is equal to A times x minus x1 times x minus x2. That's a short form for that, right? And it could be negative ones also, but that's okay. But I can count them using a natural number.
I have one concern. Going back to the point, like the statement that you made a few moments ago, when you said you have the roots, then you know everything about the function.
That's correct.
But coming back to the point there, it does not look like it, right? You have a factor there.
Constant times. I can shift the function probably. So I can up to a scale. So I know everything about the function up to a scale. I think that's probably a more accurate statement. Yeah. If you depend on that statement, yes, that's true. But then I was lose it. I think I'm. Is that?
I think this is might be just bookkeeping, but it seems to me like if you have the A inside the product, you would end up with g of x equals the product of A times B. It seems like those two are not equal. It seems like you would get A to the R.
A to the what?
So it seems like it seems like you can't pull A out of that product. Am I being silly or?
I think you can. Let's say
It looks like it might change B, like the coefficient of x.
how about this? Let me write an example, right? I'm just going by examples every time you guys are telling me. So suppose g of x is equal to 3 times sin x, right? So 3 is the A. I have to capture that. And what is this equal to? I'll say this is what are the zeros of x? X is equal to pi, right? X minus pi. That is x itself. So that's 3 times x, right? And then I need an x plus pi, x minus 2 pi, x minus 2 pi here. And I keep doing that.
Yeah, that works.
Yeah, this is completely, this is sine function. And you would say, I think this is the identity that this will be, I think this will be written as x squared minus n squared pi squared. Right? Because this is x squared minus pi squared, x squared minus 4 pi squared, and at n equal to 0. So, okay, so that's not correct. N equal to 1 to infinity plus, or then I will multiply this. So it's 3x times. I think that's better. So this captures all the roots and the factor of 3 is, I think, necessary. That's what I was trying to say. Like, how will I capture this amplitude of function?
Right.
So scale.
I think so. Mine is just about. My question is just about how you write it, I guess. Because it would, so for me, seeing like pi from R, like pi of up g of x, yeah, it seems like you're multiplying an a at every term. So it seems like it would have to be a times. Yeah.
Oh, I see. So how about this? Oh, you're saying this should be here.
Yeah, I'm just wondering.
That's yeah, how does this work?
Because
I understand, that's correct. Okay. So product of 3 times x will be 3 also is correct. Yeah, you're right. Yeah. Okay.
But if the A is inside, you can do the same thing at the end, pull it out. Apply.
Yeah. I think, but he's pointing out something I think intricate in the sense is there a difference between this, right? I think that's what
Yeah.
what's the difference between this and this? This is product, let's say x going from I equal to 1 to 2, let's say, right? Where there is no I sitting there at all. Right. So on the left hand side, I would say, since it is I equal to 1, x can come out, so this is 3x squared. And here, right? So this will be 9x squared, since there is no I sitting there inside. Right? I think that's what you find out. So since it's inside the product, you have to pull that, you have to take care of the 3. I think that's correct. Yes, I think it's correct. Yeah, I was have something intention. Okay, good point. Good point. But I think the discussion that we began with was that is this A necessary in that product need to have A as far as I see. And so in that spirit, if I were to write this, allow me. Right? So where that constant A now has probably some meaning for you to use the example of sine function. And even sine function with negative roots can be written in this form. It's just some pattern you have to cook up there. And now again, if you see derivative of g of x at x equal to xr, let's say. Right? So now there are many points where this goes to 0, but I evaluate the derivative at x equal to xr. And I say that's pretty much got by get rid of the so pretty much g of x. Am I right here? Divide it out by x minus xr. That's what I was trying to do here. I'm not sure whether I'm stating this correct. And then x equal to xr. Is that correct? Let's check.
So are you trying to get to the point where you have like del g of xi over del g of xj for the delta distribution?
No, I was just trying to do this. I was going to generalize this to any function g of x.
Okay.
So if you guys agree with this, what I would say is that, oh, I can always evaluate this. So I want to separate this. Okay, so what I want to do is, like we did there earlier, minus infinity to plus infinity, d of x, and then del of, I want to isolate x minus xr. And remember, we wrote this as plus 2a there. And here, I want to write everything else. This will be a derivative of g with respect to xr. And since we are going from minus epsilon to plus epsilon, right, and that, so what we're saying is that sum over all the roots. I'm not doing this very well. Excuse me.
Professor, I have an issue with the
Yes.
second last equation.
Second last equation here.
So if we evaluate the right hand side of the equation where x is equal
5 by
to
0.
the whole thing becomes undefined.
But I would take that cancellation first. Do the cancellation first. I think that's the tricky part, that there's a 0 over 0 there. I agree. There is a 0 over 0 there, but evaluate that, take that, make that cancellation first, and then do that. Yes, that's correct. The way I have written it, there is a 0 over 0 there, but do that cancellation. So maybe it has to be done more carefully. Oops. So I accept that. Yeah, this is what I wanted to say, but I can't modulate. confused by this.
I definitely see the pattern.
You see the pattern, but you're not convinced, right? It seems like I'm hand waving. Okay, let's do this better. Okay, I think it all boils down to this. I can state this better. Oh, I might have notes. No, I didn't bring my notes. Okay, let me try this again. Because whatever happens here is going to happen now. So g of x is x squared minus a squared. So this is that's the cancellation you're talking about. Minus a, minus a. But then I wanted to evaluate it at x equal to yeah, I think this is the point. Yeah, go ahead.
I don't know.
I think if you so visualize this way, which is of course x plus a plus x minus a. But now let's say that around, so for x less than epsilon, x less than x or minus a, right? So this is a plus epsilon to a minus epsilon. That's this region. Then derivative of x is equal to just evaluate this f x equal to a. I wrote these two functions, but then I said that derivative of g in the very close vicinity of one of the roots is nothing but the value of the function at that point. Derivative of the function, which is geometrically speaking, again, if I know this, very close to this point, it's the derivative itself. Right? It doesn't know the derivative of that point. So it's very soft statement. And I think that's all I'm trying to say, that derivative of the function f x equal to xr is now I rewrite this. So this is written as g of x, like we did the earlier case, x minus a evaluated at x equal to xr. So write this as g of x, x minus xr, and evaluate this at x equal to xr. So this seems like I'm dividing by a 0, but it's not, as Avinash pointed out, and it's clarified that there is after that cancellation. So this is true. Around, yeah, that's agree. And if that is the case, I can also proceed and say that g of x actually is equal to x minus a times derivative that correct? And product. Product of our product rate. No, sum. G of x. G of x. No, let me not say that. Yeah, that's correct. So now if I go back here and say this is what in this limit, this is nothing but x minus xr times the derivative of g with respect to xr. So that's what I'm trying to put in.
I have another question.
Yes.
Is there a reason why we have a somewhere and xr somewhere?
Because this is a specific example. Here xr is equal to plus a and minus a. Right? This is a specific example, and I'm using that pattern to make a very general statement. And since I did not come prepared, I'm struggling. Okay, so simple. Okay, but better. And from this point on, I use exactly the same relation here and say that, oh, this is nothing but sum over r. Evaluate this at x equal to xr, divided by derivative of xr at x equal to xr. And then you take the magnitude of it. So here's what I can do. I want to see if I really clarified everything or not. Let's do the following. Because we have the sine function, right? Yeah. So can we do integral dx delta? So this is extra credit, so that I know whether it's got this point. Sine of x now let's take the limit from 0 plus to infinity. The 0 plus says that I don't pick the x equal to 0 root, and I don't take any of the negative roots. I'm capturing all the positive roots, and those positive roots will contribute, and whatever that contribution is will show up here. And what is this equal to? And this should be some, just for the hint, this should be some standard Euler's, there's a constant. Think of zeta, yeah, zeta. Don't have to think of zeta function. This is a very standard series that comes out. There's a nice number there. Okay, so just to check whether how much I confused you guys. Okay, if you guys don't do this well, then I'll teach this again. If you guys get this, then I know that okay, even after all the confusion, we still managed to get the important. Yeah, sorry about that. I was wanting to start the Maxwell's equation, but that lost that. Yes. But sometimes mistakes helps, I guess. That's my only excuse I can give. Okay, thank you. And others, I think
Is there any
I like
Maxwell's-
the attendance. Huh?
is there any Maxwell's equation?
Yeah, go ahead.
Is there any Maxwell equation in the homework that is due Friday?
No, the Friday homework should be all good with what we've learned earlier. Of course, everything I have not taught. Notice that I also posted some notes, resource material right next to the homework that might be useful, but that is a lot of stuff in there. But the point is that expectation is that those are the things we will deal with. So no worries if you don't get through everything there, but you should have a feel for reading those, at least what it is asking. Like in my exam, I can pick one of those and ask. That's my point. So it doesn't mean that you have to go through everything, but you should feel comfortable doing those things. That's good. Thank you.
Thank you. I will say that I don't feel bad now when I got up and I knew what I wanted to do at the board, but somewhere between A and B, I got stuck in the mud.
I mean, it's a bad thing to do when an instructor does it because students think that this concept is hard. But I think this one, don't get that. This is my mistake. The concept is not hard. Okay, enjoy, guys.
Thank you.
Of course, then I had one professor, we had a chalkboard that went all the way across the room and all the way down. And he would get down here and catch his mistake, which was up here. And then he would go through and he'd make one correction. And then you would have to go and rewrite your notes
I know.
and do all this trick.
I know. I mean, I am myself to blame. I do this, but hopefully not too often. I do this. It's usually not being prepared. Like I've done this so many times that you think, oh, this is easy.
I understand.
And then you come back.
And there's that one thing that you forgot. Thank you.
Sorry.
So,
Jordan, yes.
yeah.
Yeah, go ahead.
So when these get more and more complicated, or is the plan to just like tailor expand, take
Yes.
first term?
Yeah, it is Taylor expansion, but this is this is not really Taylor. This is a product expansion, right?
Mhm.
Not a Taylor expansion. This is a how would you say? The root expansion. I don't know what's this called, but this is another series. But Taylor expansion should give you the same idea, except that you're to pick each point, each root, right? You're Taylor expanding around each root.
Mhm.
That's it,
Yeah.
right?
Mhm.
That's the basic idea, and that is all you need. And we won't use this until next semester.
Okay.
The explicit detailed version that I gave you, the general formula.
Okay.
We will be using the first expression, delta of x minus a is f of a. That's all we will be using.
Okay. Because it's static and dealing with like point charges.
That's correct. That's exactly what you said it correct. In statics, we won't have any problems. It's only when dynamics comes in, then I
So
worry about it.
I have a question too. So again, I guess it has something to do with the Taylor expansion, but whenever you have a bunch of charges in an area and you take a bird's eye view of it, it looks like from a distance, it looks like a point charge.
Yes.
That's when you could use the Taylor expansion then to
True.
use the leading dominant term, right?
That's correct. That's correct. That's exactly correct. Yeah.
Okay.
And we
in
will
other
do
cases,
that.
it could be more specific, like a dipole or like a,
Yeah.
whatever.
No, you said it correct. A dipole will look like no charge from very far away, right?
Yeah.
In the leading order, it will not be the charge itself. It will be the dipole that contributes. Yes, that's a very good point. Yes, exactly. That's all. This is going forward. I mean, when things start moving, then you have to have that functional dependence in there.
Mm-hmm.
That is where this is used. But for some time, we won't be moving things. We'll be doing statics. Next semester is where we will do dynamics.
Okay. Alrighty, I can deal with that.
Good.
Thank you.
Okay, good.
Have a good day. I'll see you tomorrow.
Yeah, you, yeah, see you tomorrow. That's correct.